Hello, my name is Roberto. I'm a postdoctoral researcher at the Federal University of Goiás, and I'm here to present to you my work, which title is Autonomous State Management Support in Distributed Self-Adaptive Systems. This work will be presented at the 6th workshop on self-aware computing, and this work was done with Dr. Barry Porter from Lancaster University in the UK. So the main message of this presentation is autonomous state management is completely neglected in modern distributed systems. So this talk will give you an example and try to illustrate why that is true and try to provide a way to fix this. So why do we need state management? Well, current technologies support adaptation, but they do not give you a lot of support to state management. So popular technologies such as cloud computing, edge computing, containers technologies, container orchestration technologies are all used to create adaptive distributed systems, but they leave all of this state management to the developer. So let's illustrate what do I mean by this. Okay, so it's very common to take your application and put it inside of a container. And then what you have to do is you have to take care of your state. Usually what we do is we take our state and push it towards a database, like the image illustrating. So then we have a stateless container. So you might ask, is this really realistic? Is that what we do? So widely adopted technologies nowadays, such as microservices, do exactly that. So we end up with a stateless container because we took care of the state previously. So now we're free to use all of that cool technology to create a very adaptive environment. So for example, we can take our container, deploying to a cloud provider and do horizontally scaling, like so. We can also take our container and place it in a different geographic location or change the cloud provider to save some money, or we can even push our container towards the edge to reduce latency and boost performance. So all of that cool technology nowadays make the system incredibly flexible in order to boost the system performance, increase availability, save you some money, or even optimize some other non-functional requirement, such as increased security. But nobody's actually looking into how a state can be autonomously managed. So the state currently has to be taken care by the developers. And especially, we're not looking into state management in a very fine-grained level. So what is our goal? Our goal is to enable objects in object-oriented technologies to be relocated, replicated, and have their state charted. So we're going to illustrate exactly what we mean by that. So in this picture right here, we have a representation of an object. So we have the object behavior, which are their methods. We have the state, which is the object attributes, and all of that is encapsulated. So there we have it. So let's just, for now, forget about the containers and the other popular technologies and just focus on this fine-grained picture. So what we would like to do is to be able to extract the state from the object, like so, at runtime. And by extracting the state from the behavior becomes stateless, and then we can actually replicate it as many times as we want and connect to this isolated state we just disconnected from one particular object. So by doing that, we give the system more flexibility in terms of how you can organize your objects at runtime without breaking the system. So that's actually our goal. So how do we do that? How do we support state management in that way? Well, we are here to propose a meta model that would transparently support state management for self-adaptive distributed systems. We're going to use reflection, and we're going to use component-based technology. Now, for the component-based technology, to the best of our knowledge, you can use any of the technology that is out there, and there are plenty. You can use OpenCom, Fractal, OSGI, any of them. We decided for this presentation to use Dana, and you can check out the Dana project at projectdana.com. So we chose Dana because we believe that Dana is the most advanced component-based model out there. And because it really merges the ideas of object-oriented programming and component-based models. All right, so we're going to use the reflection API provided by Dana in order to extract the state from the behavior and to instantiate new behavior, to insert the state into a newly created instance of the behavior, and so on and so forth. We're going to use the component-based capabilities of Dana in order to change the behavior at runtime without breaking the system or having to stop the system. So imagine at runtime, you change your object method implementation to a different one at runtime. So that's what we mean by that. Okay, so what we want to achieve here, we want to create this meta model that would support relocation, replication, and sharding of stateful objects. We referred the audience to have a look at our paper to really get the details of each one of these actions. We're going to illustrate only the relocation and replication one in this talk. We also have this API with a set of functions that would allow you to do all of the state management by just calling simple functions. And we're going to illustrate how those functions are used just now. Okay, so relocation. So basically what we want to do in relocation is we have an object running on machine A, and we want to, at runtime, take that object and transfer it to a different machine. So first of all, we stop the object. Stopping the object would make the state not be changed when we're doing all of the steps that are necessary to relocate it. So we just stop the object. So incoming requests are not going to be processed. So then what we do, we use reflection to create a new instance of the behavior in the different machine. We extract the state from the local object and insert it into the remote object. And then we switch the behavior of the local object to a proxy. Now, this proxy implements the same interface. Otherwise, all of the methods are the same, but the implementation is different, and it's different in a very special way. So what it does is, as incoming requests or invocation to the methods come, it just reroutes those requests to the remote object to be executed remotely. So after that, we resume the object, and there you go. We relocated the object by creating a transparent RPC. All right, and now here's the code that illustrates everything that I just mentioned. So you can use all of that functions from the API to accomplish this. So you pause the local object, you create the local proxy, then you create the remote instance, and then you extract the state, and then you insert the state in the remote instance, and then you rewire everything and resume. And that's the result. Now let's talk about replication. There are many ways of doing replication, and again, we refer the audience to take a look at our paper for a full description of each one of them. But for this presentation, we're going to focus on state isolation. So we start with an object in a local machine, as we previously mentioned. Then we pause the object again to prevent the state to be changed while we do those operations, the necessary operations to do relocation, to do replication. And then what we do is we create a proxy on a different machine. So the first step here is to isolate the state. So that's what we're doing. So this proxy will actually be the proxy that will give you access to the state that we're extracting from the local object. So once we created the proxy, what we do is we copy the state and place it into the remote created proxy. Then we replace the actual state to a local proxy. So what we created here is every time you call a function on the behavior on the local machine, and that behavior changes the state of the local object, what it does is when it access one of the attributes, instead of changing the attribute locally, that request gets rerouted and sent to a different machine, to this proxy. And then this proxy will actually change the state in a different machine. So we transparently created an RPC to change the state. So now what we did was we extracted the state into a different machine, leaving the behavior, the original behavior, stateless to be freely replicated. So that's what we do. We replicated as many replicas as we want. In this case, we created 2 different replicas of the behavior into different machines. Then we copied the proxy of the state into the remote replicas we just created. And once we did that, what we do is we change the original object into the proxy. So now we created a bunch of different transparent RPCs and we resume the object. So let's take a look at what's going on here. So local function calls gets to the object and then it gets to a proxy. The proxy will reroute the function call to the actual object behavior, which will happen, the process will happen in this machine. But then if the function, the method wants to change the state, what ends up happening is that it tries to change into the proxy, but then that gets transparently rerouted to the actual place where the state is located, where the state will actually be changed, right? So then a function that was supposed to execute here gets rerouted and executed here, and the state gets changed over here. So then you can create as many replicas as you want. And if your behavior is very CPU intensive, you can boost your system performance by creating many different instances of it, you know, and supporting horizontal scaling. So that's the picture of what we just did. We isolated the state, and then we can actually replicate the behavior as many as we want. So here is the actual code to do that. So the top side of the code just illustrate how you stop the object and then how you create the local proxy and the remote instance of the state at first, and then you create all of the proxies, the local proxies and the remote proxies of the behavior of the object, and then you wire everything up with the functions at the bottom of the picture. All right, so to conclude, I just want to remark that autonomous state management is completely neglected from modern distributed systems. State is often manually and carefully handled to create stateless containers to support adaptive systems. And we presented a meta model and an API to support transparent state management. Our meta model enabled distributed stateful self-adaptive systems to be organized at runtime. My name is Roberto. Thank you very much for watching. And if you have any questions, feel free to contact me using the email address down below. Thank you very much.